my contribution to the M word, the millennium word. It was taken from my clock on 1st of January 2000. And that last one at 5:20. Now, we're quite used to that sort of change. That happens all the time around us. We're used to daily change. We're used to weekly change. We're used to even decadal change, maybe even centurial change. But one of the problems is that when you're dealing with rocks, the time spans of change are far beyond our 10. And so therefore it's very difficult to see what is actually happening in geology without lots and lots of information going in. And the general public don't see that change. So I remember a story told by J.G. Ballard, a prominent geologist from the USA. And he was saying, I take the analogy of the butterfly and the sequoia. The butterfly, you ask the butterfly, is the sequoia alive? And the butterfly says, well, no, I've been here all my life, 4 days, and it hasn't changed a bit, so it can't be alive. Similarly, our 70 years on the surface of this planet doesn't see the sort of change that occurs in the Earth's time frame. So Kay asked me to talk about something I was interested in. And so I thought, oh, well, I'll talk about something I've been interested in for most of my life. I actually looked back at my catalogue of my own personal collection, and the date of collection on the first entry in my catalogue is dated 1957 when I was 5. The actual notation wasn't made then, but the collection was. And marry it with something that I've been interested in for 40 years since we moved to Warwick from elsewhere in Queensland. And to put them together, what is the geological history of the Southern Darling Downs? So how it came to look like that. Now that's taken from the southwest of Warwick, looking over the Warwick, You can see a couple of things in there. The first one, that's better. The first one, which I'll come back to, is Mount Tabor, just outside Warwick there. And you can see the characteristic flat top. You can actually see the gap, which is there in behind the southern, okay, and the flat topped mountains, which are to the east of us. And I'll come back to that a little later. Okay, so let's get our bearings. Okay, I'm not going to enter into where the Darling Downs is, because when Alan Cunningham described it in 1827, it was quite a restricted little area just to the northeast of the town, and now it seems to have spread a little bit to places quite a lot distant. Okay, so my map and where I'm going to be talking spreads as far north as Allara, as far south as Dalveen, as far as east as the Escarpment, and as far west as Pratton. And all of the area, all of the rocks in here come from that area. Okay, as far as the history is concerned, we're the young fry. Most of Australia has a long, long geological history. In fact, we have one of the oldest histories in the world. We have the oldest rock reliably dated. There's a sandstone in Jack Hills in Western Australia, dated at 4.4 thousand million years. Now that's only 100 million years after the original formation of the Earth. And it's here in Western Australia. We have the first reliable evidence of life on Earth, stromatolites, 3.84 thousand million years in Western Australia. We have those unique fossils in the Ediacara Hills in South Australia at 635 million years, which are the first evidence of multicellular life on Earth. Okay, and most of the core of the Australian continent was actually formed prior to 1600 million years, and almost all of it before 1,000 million years. So the history in Warwick only goes back to 380 million years. So we're the add-ons, we're the afterthoughts, okay? In this slide, you can see where you've got the continent, the main core of the continent out to the west, and then you've got various bits which sedimentary activity and igneous activity have pasted on to the east side of the continent, going from about 700 million years to 540 million years, back to 300 and then there's a little bit which is a little later. Okay, so back to the specific topic today, the geology of Warwick. The first recorded activity is about 380 million years ago, right? When violent eruptions produced tuff, you know, very similar to what we've got in the Kangaroo Point Hills, Kangaroo Point cliffs, where an explosive volcano goes boom, all the ash drops. Sometimes it's hot enough, as it is in Brisbane, to weld it together. Sometimes it's not. In Warwick it wasn't, and it's quite soft, where it's that tuff is quite soft in Warwick, whereas it's hard as all get out. I grew up in Brisbane, so I know just how hard Brisbane tuff is. And there is 1.8 kilometres vertical of this stuff. There's tuff, there's agglomerate, there's a few marine sediments. Then there's a bit of a break, and about 373 million years, there's a similar organisation of stuff where there's a lot of this volcanic activity and marine stuff. And then another little tiny break, and then 371 million years, you've got a much quieter, lots of marine sediments, and just a little bit of volcanic stuff. So I hope you're not bored at the stage, because now I'm going to ask you to get on your feet. And if you'd like to come, pardon me to the Zoom people, if you'd like to come and take a sample of that rock in here, this one down the front closest to me, thanks.
Exercise, yeah.
Yeah. Oh, you'll get a lot of exercise, Chris.
What area was that? Where was that? You were saying where was this?
Sorry. Oh, we're southwest. We're 2 hours southwest of Brisbane.
Oh, but where was this one relative to Warwick?
Oh, yeah. These are all the samples are within 25 kilometres of Warwick. Could you just pass me the big sample down on the corner, thanks, so that I can show it to the Zoom people?
Paul, you got one?
Right. Now, the rock that you have is different to the one that is on the slide at the moment. The one on the slide is, the photo is taken just below the spillway of Connolly Dam. It's quite hard. It's been heated, it's been compressed, it's been generally mashed about. The outcrop of these sorts of rocks is fairly complicated. It's very, very hard. It gives high slope and spur and gully terrain. Chris will understand spur and gully terrain. Okay, so we're talking about the period 380 to 370 million years. Okay, now I'd like you to look in careful at the rock, particularly if you've got a hand lens. Any magnifying glass or hand lens? Okay. I hope that email went out, didn't it?
No.
Oh, didn't it? Oh, okay. Look carefully. Okay, at your rock. Roll it.
A magnifying glass on your phone, actually.
That's true. Roll it around. Okay. Do you see the little glints?
Yeah.
Okay. What does that tell you about the rock? Yeah, minerals, it's got crystals there. Now, if a rock has crystals, what sort of rock are you looking at? Yeah, well, it's either metamorphic or igneous. It's certainly not sedimentary because you'd expect particles rather than crystals in a sedimentary rock. Okay, so yes, it is igneous. Is the crystal size large or small? Small, and so therefore, if it's igneous, then you're expecting very fast cooling, probably on the surface. If it's metamorphic, you can't really tell anything because the growth of the crystals may have been limited by the parts of the rock around it. So you can't say anything there. Okay, so therefore, we've got crystals, we've got igneous or metamorphic, we've got very fine crystals, fast cooling, we think. Okay, it's got a dark colour, obviously. Okay, now if it's igneous and igneous or metamorphic, the dark colour normally points to it having a high amount of iron and magnesium. And that's quite true of this. Okay, so in the photo I've taken here, have a look at the patterning of the quartz veins, which have come from metamorphism. Have a look at the patterning, particularly down in the lower half of the photo. And you will see that all of the quartz veins are oriented in those directions. Now that roughly 60-degree angle between those quartz veins tells you that the rock is very stressed. It's been compressed, it's been sheared, and the weakness planes that have developed have had quartz shot into it. And so therefore we can say probably metamorphic therefore, okay, because that quartz only comes with probably igneous bodies around. Now the rock type is an andesite, originally anyway, okay? Now you may be able to identify some part of the world that an andesite was originally named for, okay? It's named for the Andes, okay? And one of the popular conceptions is that this sort of eruption occurs in what we commonly call the Ring of Fire, but which is also called the andesite circle. And so therefore, what we now need to look at is, well, how did this actually get there as an andesite? Okay, there are some fossils in the marine sediments. This is an example, okay? This one was dug out of the Elbow Valley lime pit, and we very occasionally find these fossils. It's fairly well cooked up by later igneous activity. But the interesting thing, well, no, the unfortunate thing is, why are they digging this limestone out of the Elbow Valley lime pit? It's laying supplement for chooks. Okay, so what I'd like to do is I'd like to digress slightly now and talk about something that's fairly basic to geology. We weren't here 380 million years ago. We weren't even here 1 million years ago. And so in about 1830, Charles Lyell, one of the fathers of geology, stated what we actually had to assume. The assumption is that, and he stated quite nicely, if you see a feature in geology being produced in the modern day, and you see that same feature preserved in the rocks from previous eras, we assume that they are caused by the same process. We assume that the Earth acts in consistent ways over long periods of time. Okay? Without that assumption, geology makes no sense whatsoever. Okay? Now, the assumption is not valid. Well, no, it's not valid beyond about 2.3, maybe 2.5 thousand million years. The Earth will only operate in a consistent way if the chemistry and the physics that control geology remains the same. And before 2.3 thousand million years, it was not, because we did not have an oxygen atmosphere. The oxygen atmosphere only came from the first oxygen shock about that time. Before then, the atmosphere and the oceans were completely different in their chemical organisation, and so therefore we cannot necessarily assume that the same things were formed before then. But the Earth has been somewhat similar to that since then. And since we're only talking about 380 million years, we can assume that what we see in Elbow Valley here with the corals and with the andesite, that was formed in the same way as we see it being formed today around the world. So, okay, we see the corals and the crinoids. What does that tell us about the environment? It tells where do corals grow today? They grow in warm, shallow, marine situations, which are fairly calm. And there's also volcanics involved there. If we go looking around places like Indonesia, okay, or Japan, okay, so this is what we believe the seabed would look like about 380 million years ago. You've got your corals, that's a coral there, that's another coral there. These are solitary corals over here. You've got crinoids, okay, crinoids up here. They look like sea lilies, but they're not plants. They're actually sea urchins turned upside down and put on stems, okay. They're very definitely animals, echinoderms, okay. And you've got trilobites, distantly related to present-day horseshoe crabs, okay. And you've got the predators of the time, which are the nautiloids, there and there. So that's what the coral reef around Elbow Valley would have looked like about somewhere between 370 and 380 million years ago. The overall landscape probably looked like this. That's an andesitic volcano with a black sand beach, okay? And so therefore, working on Lyell's uniformity of process principle, how did that landscape form, and how does that inform us about what happened around Warwick 380 million years ago? The present situation in Japan looks like this. It's a subduction zone. It's a convergent plate margin where the Pacific plate is being driven by new material being formed at the mid-ocean ridge, pushed sideways, and when the plate gets to the Asian continent, you have the immovable object and the irresistible force. Which one gives? Well, it's actually the Pacific plate, because the Pacific plate is denser than the continental material and is forced to slide underneath the Asian plate in a process that we now know as subduction. Okay, so the oceanic plate is sliding underneath. As it slides underneath, the marine sediments and the volcanics, which have accumulated on the ocean floor, are scraped off into an accretionary wedge in here. Okay, and the massive friction involved in this, plus the heat from the interior of the Earth, melts some of that, and that's made easy because, of course, this stuff's wet. It comes off the ocean floor. And as a result of that, okay, we have rising molten rock, magma. Sometimes it gets to the surface and we have an andesitic eruption. Oh, and sometimes it doesn't quite get that far and it cools slowly deep within the Earth, 1.5 kilometers or greater. Okay, so that's the basic picture of what we think happened 380 million years ago, not just in Warwick, but along the whole of the present east coast of Australia. And I'll get to that in a moment. There was then a short break, okay, and to the south and west of the town we accumulated an enormous amount of conglomerate, sandstone, chert, some volcanics, limestone. Now, in the actual picture there, I've got an area in lighter grey. This has now been replaced by other rock, but we're fairly certain that there was this type of rock, the Texas beds, in that originally. Okay, and we're talking about 350 million years. Okay, now at this stage, since you're now getting bored again, how could I ask you to get up, return those specimens to whence they came, and take a sample of the Texas beds.
We're going to get us to keep them and remember.
Oh,
what
you
they
can
were.
if you like. You can if you like. Okay, what's the name of that rock? Don't forget.
Ansonia.
Don't forget that there will be a test at the end of the day.
We're gonna use this back in the different bag.
They're pretty obvious which ones are which. Oh, okay. There is a larger sample of the Texas beds in the bag. Could
Big one.
could you grab the big one for me, thanks? So I can show the little bit. Thank you. For the Zoom people. Okay. Right. For the Zoom people, I hope that that's in focus. I don't know where the limit of focus of this camera is, but this is what the people in the room are looking at. On the screen, you will see that it's very rocky, it's very hard. It's commonly called trap rock around there. There are two explanations for why it's called trap rock. The first one is that the Norwegian term for black is trappa, and there's an awful lot of black rock in this particular area. But also you can see that it breaks up into blocks which are 5 to 10 centimetres in size, and it's just the right size to trap the hoof of a beast. So we're not quite sure why it was originally called trap rock, but you can see that it's very hard and it's very rocky. Okay, there are some fossils, particularly crinoids as shown, and corals are found. So the seafloor probably looked like that. Okay, so we're now talking 360 to 340 million years during the Carboniferous period, when the Northern Hemisphere had lots of coal being formed. Okay, right, have a look at your rock. Can you see anything?
Rock.
Can you see any particles or crystals? Does it glint? No, and that's a fair giveaway for the fact that they're particles. So therefore, it's pretty obviously sedimentary. Okay, they're very fine grains. You can't actually see them, can you? Not with the naked eye anyway. Okay, what does that tell you about the environment of formation? Yeah, calm, violent, what? Calm, yes, very calm. Okay, what does that, okay, it's mainly made of quartz. You won't be able to see that, okay, and it's a rock called chert. Now, the interesting thing about chert, excuse me, Zoom people, the interesting thing about chert is that the minerals in it tell us that it was formed under reasonable pressure in cold climate. Okay. And so therefore, where's the obvious place that a sedimentary rock would form in cold water under high water pressure? Well, certainly on the seabed, very deep, right? Okay, oh, it's steep and rocky, okay. But we've got coral fossils. Where do corals form? Okay, a paradox. A paradox, a most unusual paradox. There's enough of Gilbert and Sullivan. Okay, so we have a paradox here. We have a combination of things which we know, no, sorry, we assume are formed in shallow water, and we have it in a rock which is only formed in very deep water. Okay, so we have to reconcile those two paradoxical things. Deep marine, calm fossils from the continental shelf. What we think has happened here is another characteristic of a convergent continental margin. One of the things, the massive friction between the underlying oceanic plate and the continental plate is that it doesn't just flow smoothly, it goes in jerks. And those jerks, okay, the earthquakes shock fluidized sediment on the continental shelf. Okay, everyone's been at the beach where they've stamped on the ground just close to the water and the sand goes all flubby and the water comes to the surface. That's called shock fluidization. This happens big time when literally cubic kilometers of this sediment is shock fluidized, rolls off the continental shelf, down, gouging big canyons in the continental slope, and deposits itself as a fan of material in the deep ocean, with deep ocean marine sediments and the unfortunate organisms that have been dragged off the continental shelf and down into the deep ocean. And that's our interpretation of this so-called paradoxical rock. Okay, these currents, by the way, have actually been observed by the US Geological Survey. They set up some cameras on the canyons that they identified off the east coast, the Atlantic coast of the USA, and they actually, and after a small earthquake up around Newfoundland, they actually saw one of these currents going through, a turbidity current, moving at about 70 kilometres an hour. It doesn't mix with the rest of the seawater because of the difference in density, because of, between just plain old seawater and seawater plus a whole lot of other stuff. Okay, around 300 million years, the currents deep in the earth that were driving this convection, they stalled, they moved elsewhere. And so the subduction zone started to clog up. That led to a whole lot of force rearrangement in the crust. And so therefore, the next lot of rocks just south of town are isolated little blocks, used to be continuous, but now those forces have broken it up into smaller bits. One of the most interesting is about here. Okay, and it's called the Eurodesma beds. Now, Eurodesma is a bivalve. That's a Eurodesma. Okay, it's about that size. Okay, but you can see just how thick the shell is in this particular sample. Now, understanding that there are very few fish with teeth at this point in the Earth's history, what would be the obvious assumption about a shell which has a shellfish which has a thick shell? It has to be protected against something. If it's not fish, what is it? I think it probably has to be a fairly violent shoreline. If you think about then that means that you've got an enormous ocean to the east of us. The primordial Pacific Ocean has just opened up because Pangaea has started to break up, and we've got this got a large ocean with prevailing winds driving very high waves onto the Australian eastern coast. Okay, you can see how it's limestone. Okay, you can see just how rich this is. Okay, all that light grey stuff is shell. Okay, so this was absolutely crawling with life. Here's another example from about 4.5 kilometres from that where that sample was. Okay, and you can see bryozoans, sea fans. You can see bivalve mollusks, and you can see brachiopod bivalves here. And it's absolutely crawling with life. The rocks are quite soft, and so therefore we have a very low slope landform in the area. Now, how do we think that this area got? As the subduction clogged up, we had forces of readjustment. Some of the crust was stretched, and as a result, areas dropped down, subsided. The sea invaded these areas, you know, sort of isolated little areas, and therefore we get lots of little pockets of marine sediments, and there's still some andesitic eruptions going on. Okay. In addition to that, there's also sideways movement. This is all as a result of this clogging up of the subduction zone, and our part of Australia, this part as well, is being sheared southwards against the existing Australian continent to the west. So now we believe that the Texas beds and these 8 Mile Creek beds are very close to where the shear is, and I've marked it as a little rectangle there. What that does is the existing rocks therefore become even more stressed than they have been previously. Okay, so the 3 stages we've got to 250 million years ago or so. We've got the mixture of volcanic and sedimentary rocks to the south of town around Silverwood. We've then got the deep ocean sediments, the paradoxical ones, the Texas beds to the west. We've got these little pockets of coastal stuff and little bits of volcanic. But almost immediately, okay, things get disrupted and we end up with granitic intrusions. Now, this is not uncommon. Because the subduction zone has moved elsewhere, not actually moved elsewhere, it's just stopped, then this intrusion of granites, yeah, thought I'd turned it off. This intrusion is happening all up and down the eastern coast of Australia, from Possession Island, where there's a little gold mine, okay, all the way down through our area, where we've got the granite belt, the New England tableland, you've got the Enoggera granites here, okay, all the way down to the Rosebery mineral fields of northeastern Tasmania. Okay, the same thing is happening at much the same time all the way along. Okay. Okay, so this is what the landscape basically looks like with the tours. Okay. It's all happening, isn't it? Okay. Now the tours are quite characteristic here because as the remember that these rocks are formed 1.5 to 3 kilometres below the surface of the Earth, and as the stuff gets eroded off the top, it unloads and it cracks, and it basically cracks into three planes, 2 vertical, one horizontal, forms cubes. Now, at the corners of these cubes, of course, weathering processes can attack from 3 directions. So the weathering speed is quite fast. At the edges, there's two surfaces which are being attacked, and so therefore they retreat a little bit slower. On the faces, well, they're only being attacked from one surface, and so they don't retreat very fast at all. So you have a rounding effect, and that naturally produces the round surfaces that round shapes that you have in the tours. Okay, right. Now, time to get rid of the boredom. This time, it's a harder one. If you wouldn't mind returning your Texas beds to the appropriate bag, so I can use it to talk. and take an example out of each of the 3 bags in a row. Thanks. Oh, sorry. There you go. 10:40 already. Now,
Well, they give enough.
I know. There is a trap for the unwary here. Do you know which bag the black and white one came from?
I remember which bag we're taking them out of.
It actually does matter. It's different. They're different. Okay.
Well, we'll have to
But,
remember.
oh, well, no, it's not particular. I know which ones are which. Have a pink sample. This is what people are looking for. Oh, okay. That gives quite a nice picture for the Zoom people. Okay. Right. Now we're looking at the period from the Permian to the Triassic, mainly in the Triassic, about 280 to 225 million years ago. Here are your 3 rocks. Can you tell the difference? Okay. The one on the left-hand side, which is just a shade darker, is called the grey granodiorite. The one which is just a shade lighter is called the Stanthorpe granite. It's got another technical name, but let's just call it granite. Okay, and the pinky one, and you should no prizes for guessing which one that is the Ruby Creek granite. Okay, so yeah. Not easy to pick the black and white ones, is it? Okay, so first of all, is it crystals or particles? Okay, so obviously it's igneous, isn't it? Okay, are they large or small by comparison? They're large. Okay, what does that tell us about the rate of cooling? Slow cooling, and basically you're talking about a blanket of earth over the top of this, formed 1.5 to perhaps 3 kilometers deep in the earth. Okay, so it's light color. That means there's a fair amount of quartz. Okay, and the rock type is granite. And I know there are other terms. You know, there's what I've called the Stanthorpe granite is technically the Stanthorpe leucoadamalite, but we won't worry about that. Let's call them all granites. Okay, they're all formed by the same process, and they're all the direct result of the clogging up of the subduction zone. Now, we've got low slopes, and we've got granite tors. Okay, we've got sandy soil. Okay, we've also got, and the Ruby Creek granite is the important bit here. We've got lots of economic minerals here. That's a nugget that I found just west of Pratton about 1984. I think I was out there with my class. Yeah, they actually found bits of gold too. Okay, it's taken from the vicinity of the Big Hill mine. Okay, now the mining of Big Hill was very easy. It's actually a dike that's been shot up through the existing rock, and the gold is in the edges of there. So all you do is you pick it out and you let it drop down to the bottom, and you drag it out at the bottom. Let gravity do your collection down the bottom. As long as you remember to shore up so the walls don't fall in on you. Okay. Now we're talking about gold, we're talking about tin, we're talking about silver, we're talking about lead, we're talking about manganese, you name it, the area has it. Okay, so the local importance of gold, tin, silver, lead, copper, all found near the Ruby Creek granite. Okay, concentrated in what we call the last melt fluids. Now, the age of the Ruby Creek granite is important here because it's the last one. Okay. When you've got a magma chamber, the minerals which have the highest melting point crystallize out first, and they are characteristically the ones that are rich in iron and magnesium, and are the black ones that you can see in the two salt and pepper samples. Okay, there's hornblende, there's augite, there's biotite, and the white stuff is the higher temperature feldspars. Now, all of these minerals have very specific chemical compositions, and so as they crystallize out, they scavenge those materials out of the melt, and therefore the chemical composition of the melted rock changes. So the one magma chamber will give you different rocks over periods of time. Okay, so we go from the grey mare granodiorite, which is the slightly darker one there with slightly more dark mineral, and then the iron and magnesium get scavenged out. And then we go to the Stanthorpe granite, which has a little less of that and a bit more of the white feldspar. And then you go, once all of that has been scavenged out of the melt, you end up with the sodium and potassium and lots of, and that's the pink feldspar that you can see in the Ruby Creek granite. And you end up with a lot of quartz, and you end up, because this originally came from marine sediments, you end up with a lot of water. And that water carries the good stuff. Gold, silver, lead, manganese, they all have big atoms, and those big atoms do not fit neatly into the very tight crystal networks of these previous minerals. And so therefore, in a reverse process from the scavenging, they are shunted off. They're never incorporated into the minerals, and so the earth naturally concentrates all those into the last melt fluids. And that's what the technical term for this stuff is. And that's why the age of the Ruby Creek granite, which is associated with all of this mineralization, is important. Okay, so we now move on. The picture about 200 million years ago is one, volcanics, etc. in Silverwood. Then we've got the Texas beds. Then we've got the marine stuff all in little blocks. Then we've got the granites. And then it all calmed down and we had a big river. So once again, now, can you remember which bag the grey mare granodiorite went into? I'd invite you to return them. Don't worry about it, really. Return those to the table, and would you like to take a sample from the next one up the table labelled Jurassic? It isn't really a big deal. I can identify the different rocks.
Thank you.
Oh, yes.
We have to take something else down.
Yes.
Yeah, the Jurassic background.
Okay, yep, the Jurassic stuff there. Okay, right, here's a picture of the sandstone that you've got in your hands, okay, in a rock cutting. Oh, main roads are really good to geologists. They cut these big slots through hills and expose the rocks for us. It's fabulous. Okay, but it's interesting if you look really carefully at this outcrop, okay, it's all got lines in it. And they don't all go in the same direction. Now, this is a dead giveaway. Where obviously there is something changed between the red beds. Oh, by the way, the stuff at the bottom has to be the earlier stuff and the stuff because the new rock gets laid on top. Okay, so the earlier stuff is being laid down And now I'd ask you to look at your sample. Is it made up of crystals or particles? Particles, so it's sedimentary, okay? They are actually quite large by comparison with the chert, aren't they? So we've got moderate current involved here. And this sort of changing layering that you see in front of you here is a dead giveaway for the currents moving about. In other words, a river as it drifts backwards and forwards across its floodplain. It's called current bedding. And I can see current bedding happening in the Condamine River close to me in Warwick. Okay, so we're now talking about 160 million years ago. Okay, we've got particles with lots of layers. It's sedimentary, sand-sized grains, moderate currents. Okay, it's a light colour. Now, I haven't talked about that. Light colour in sedimentary rocks usually means there's no carbon there. In other words, no plants. Now, that's a bit of a problem because in addition to that, we've got lots of this stuff and this stuff. I found that in our backyard, actually. It's petrified wood. So there were plants there. So it's not lack of plants that's causing the light colour. It's the fact that this is an area, the plants are not being preserved in a carbon form. They're mainly rotting away. So it must have been on the surface where lots of oxygen is available for the decomposition. Okay. And okay, so we think that there was actually a fairly big forest in the area. Okay, few plants or lots of oxygen, and we think in this particular case lots of oxygen. We've got current bedding, therefore variable currents, and therefore it's a sandstone. It's a river, it's moist, we've got petrified wood or forest. Plants, there are plants there, that's what the evidence says, but the oxygen is available, and so therefore we're looking at the surface of the Earth. One of the things that I haven't mentioned is that this sandstone is very much used around the Downs. Okay, and we even have an area called freestone. Some of you may know that the old stonemason name for building sandstone is freestone, and there was lots of that mined around Warwick at the time. This is Glengullen Homestead, by the way. Okay, that's the Yangan quarry, taken in 1925. That quarry is still operational. Okay, so following immediately on that, the river slows down, and on top of the sandstones, and unfortunately these rocks are now very soft and it's very difficult to get outcrop, a very soft shale is laid down over the top. We've got lots of plant fossils through there, so it was still quite prolific in terms of the vegetation, and because there was a lot being deposited, the available oxygen ran out, and some of these plants are now preserved as just carbon, which we thankfully call coal. That, oh, by the way, that's the Mount Colliery coal mine at just up from Tanimorel. 1.25 million tonnes of coal was mined out of there between 1887 and 1968. Why did they stop in 1968? There's still plenty of coal there, and the coal runs under Warwick as well. The reason is that the railways stopped using steam engines, went to diesel. Okay, so Jurassic when, rivers and lake, warm and moist, coal at Mount Colliery. Warm, moist climate produces swamps with little oxygen in the water, so that the carbon is retained against the previous period where there was more oxygen available or less plants. We don't know which. Okay, formation of coal. Okay, so there's the pattern at the moment. Okay, we had eroded back to a surface which would have looked like that about 30 million years ago. Okay, and we'll keep the colours. And now up to 25 million years. And Yeah, right. And then, okay, we had massive eruptions down your way rather than ours, but impacting ours. These are basaltic, okay, and if you'd now like to have a look at a sample of the basaltic stuff, then it's the final bag on here. And this is what they're all looking at. Okay, same thing. Crystals or particles? Crystals. You move around in the light. You'll see the little glints. Okay, are they small, large? What? Small. Therefore, okay, it's igneous. Obviously igneous, right? Crystals. It's igneous. Small crystals, cooled on the surface. Dark color. Lots of iron and magnesium. Okay. There's very little quartz indeed in this, okay? The rock type is basalt. That'll be of no surprise to anyone in the room, okay? The environment is a volcanic one. Now, the interesting thing is that there are three foci, of volcanic eruption at this time, about 25 million years ago. You've got the Mount Warning Shield volcano, you've got the Mugara Peaks, and you've got the Bunya Mountains, which is a fissure eruption, okay? It's all basalt, okay? It's all fairly fine, all fairly runny. And so therefore, in particular from the Mugara Peaks and Mount Warning, in our area, the basalt runs up the existing streams which are flowing to the coast eastward, okay? And so therefore we have a landscape which is looking like that, and a big volcano sitting here running its basalt up the slope. That means that it sticks to the gullies. Now, basalt is more resistant to weathering than the soft shales of the Walloon coal measures or the sandstones of the Marburg sandstone, and so they get eroded first before the basalt. So where the gullies were 25 million years ago are now the ridges in our landscape. So we've got what's called a reverse topography. Okay, so what I've done, I've plotted the basaltic eruptions down the east coast of Australia over the last 40 million. These 23 are okay. As you can see, the age of the basaltic eruptions decreases as we go southward. Now, that means, what is the source of this? Well, the source of it is very deep in the earth, so it's less likely to move than we know that Australia is drifting northward. And so what's happening is that Australia is drifting northward over what we call a hotspot, a convection uprising, where it finds a little bit of a weakness. Then the basalt will come through, and then come through, and then come through as Australia drifts northwards. Okay, so what do we have? Well, you can. I go back to my initial slide where I pointed out the flat tops of the hills, which are the tops of basalt flows. Okay, you can see there are different layers in there, and particularly in here, you can see the layering in the basalt, and the basalts are of different hardnesses. Some of you will have little bubbles in your sample, others will not. Okay, there's a wide variety of the basalts up there. This one had bubbles probably of rotten egg gas, I guess. It wouldn't have been air, not coming from deep in the earth. Okay, and you can see the layers just beyond my wife. I had to put her in there. Okay, after that, we've had a very calm period of time. Australia has weathered. This is the Condamine River at Murray's Bridge, just east of Warwick. Okay, you can see the meander. You know, it's old rivers that develop curves, unlike humans. Okay, one little feature is out at Freestone. Now, this is the old topo 1 to 50,000 topo map, and the area I'm talking about is here. Okay, when I enlarge it, okay, this is Glengullen Creek. Now, it has its headwaters. You can't see the headwaters, but it has its headwaters up near the gap, close to the range where there's a fair bit of water. It has an erosion advantage over Freestone Creek, which has quite a small catchment. And so therefore what it did, Glengullen Creek eroded its way through Eastman's Ridge there to form a little river capture gorge called Freestone Gorge, okay, and leaving the dry gully, which we now call Campbell's Gully. Okay, so there's an actual river capture, happened probably 10 to 15,000 years ago. As well as that, okay, we've got the escarpment. I've finalised my landscape of the area. The escarpment has no geological reason for it at all. It's a pure erosion scarp. Okay, if we look at the isophyte map of Australia, then you will see that, well, no prizes for guessing, it gets drier as we go to the inland. But if we look at the particular area, you'll see that Warwick is situated in a partial rain shadow. The prevailing southeasterlies, which is where we get our rain from, are actually scavenged of their moisture by the higher hills of the Clarence and Richmond ranges. And so therefore, the ability of the coastal streams to erode is vastly different to the ability of the streams on our western side of the range to erode. And so therefore, we have that scarp, which is just where the erosion has happened to get to at this stage. So just in recapping it, okay, we go through lots of volcanic activity, lots of sedimentary activity. The interesting thing is you've got a really complicated picture around Warwick, which is, it's a geological jigsaw. And from my point of view, there's always something which can pique my geological interest. Thank you. You've got it? Okay, questions?
Just hold on with the questions, I'll give you the microphone, thank you.
Thank you, Stuart. Was there any evidence of the volcano or the original, like taking the graph back?
Sorry, I'm not.
Was there any evidence today of the volcano that erupted a long time before these more recent ones?
Oh, no, it's long gone. I'm sorry, I'll qualify that answer. There possibly is, but it's almost certainly covered by consequential igneous geological activity, particularly Marburg sandstone. Remember, the Marburg sandstone is really just a member of the Great Artesian Basin sediments. And it covers so much of Australia that a lot of the basement material isn't really visible to us. So maybe there, okay, but we haven't found it. The ones more recently, the 23 million years, well, they're pretty obvious around the landscape, aren't they?
Well, where are the hotspots?
Sorry?
Where are the hotspots?
Actually, it's interesting. Yes, it's interesting you mentioned that, because recently Geoscience Australia has detected hot springs on the on the seabed west of Tasmania. And that's where we would probably expect it to be at this stage if it was still active. So maybe it is, but fairly minor. Hopefully we're not going to get another volcanic eruption down there. Might be enough to...
John? Hang on.
Yep.
I just wanted to clarify which volcano you're talking about. There was, I believe, you showed those moving volcanoes from about 2 million years ago.
Yes.
But you didn't actually, they didn't go south. I believe that that's the volcanic area that goes down through.
There are. Well,
that would be the one that's now at that Tasmania.
yes.
Is that 300 million years ago or 30 million?
No, that's 30 million years ago. And those volcanoes that are in the western part of Victoria, through those basaltic plains, they should be on there, but I didn't have information, and you know, you could run down there and bore you forever. Other questions?
Just on the rock side, I think I just I think a second. The up in the gem fields there, they're talking about leverite. You heard of leverite up there?
No, I can't say I have.
So when they go around often, they can find good gemstones on the ground. If they pick up a rock, there's nothing to leave right where it was.
Hardly surprising. I haven't heard of that one before. Other questions? Anyone?
Coming to the basalt, is there much evidence of talk, basaltic talk around the Warwick area or the Southern Down?
Yeah, we haven't actually got much evidence of the basalt remaining. It's really just little bits stuck on the top of the spurs. The answer is yes. Up Goombra Valley, where you've got the Cascades walk, there is a scoria there, which is basically just a large particle, tuff, I guess. Okay, so there is some there, and it's and as well as that, there's also a trachyte intrusion. When the big volcano was starting to simmer down, I suppose, and the top got clogged, then there was intrusion between the layers horizontally from the actual conduit. And it's that trachyte, which was more slowly cooled than the basalt that was spewed out on the surface, that is the harder bit, and it's the one that produces the hard layer over a softer layer underneath that produces Queen Mary's Falls and Dag's Falls and Brown's Falls and Hoffman's Falls and all the little falls down Goombra. So yes, there is a wide variation in the basalt that we see up there.